franc praise. He is professor in l'Université Paris-Sud, France. On this occasion, Professor Patrick Gerard will give the talk entitled Explicit Formula for a Class of Integrable Partial Differential Equation and Application. Welcome, Professor Patrick Gerard, and you can start.
Thank you very much. Thank you for this great introduction, and thank you for your kind invitation. It's a great pleasure to take part in this important event for the whole of South America. And I'm very proud to contribute to this. So it's also quite a pleasure to talk after Monica Vijan, because she paved the way, in some sense, to my talk, making a very nice introduction to integrable PDEs. So I'm going to talk about integrable PDEs as well, but I will have a slightly different goal. My goal will be, in fact, also following an answer by Percy Deft about what is an integrable PDE. So his answer, it was at some different time, I think it was in Ascona more than 10 years ago. He said, okay, an integral PDE, well, that's just a PDE that you can integrate. Okay, meaning that you can calculate the solution. So in some sense, my talk today will be to stick as much as possible to this definition by Percy Deft in a class of integrable PDEs. So let me start with this class of integrable PDEs. So my introduction here is just to tell you again about what is more or less the context of integrable PDEs. I'm emphasizing this Lax pair identity that Monica Vijan discussed a lot during her talk, which is really one of the expression of the integrability, even if it's not so the whole story, because some Lax pair identity may be completely trivial and do not lead to interesting information. But in a number of cases, they really lead to a technique for calculating explicitly the solution. And since the late 60s, the technique for that was related to what we call inverse spectral theory. So the most famous example, as was recalled by Monica Vijan, is this Korteweg-de Vries equation and the Lax pair identity due to Peter Lax in that case. So this is exactly the same, I think the same notation as Monica, except that U is replacing Q. Okay, and so I'm not going to talk about Korteweg-de Vries for some reason that will appear soon. In fact, among this class of integrable PDEs, some equation have some special some specificity because they enjoy a Lax pair posed on the Hardy space. So the Hardy space here is just the closed subspace H of L2 of R, which is just a space of function square summable on the line, such that the Fourier transform is 0 for negative wave numbers. So f hat, if you prefer, is supported in the half line C non-negative. And it turns out that the equations I would like to talk about have Lax pair operators, so L, the Lax operator, and B, which is in Monica rather called P for Peter. Okay, so the second part of the Lax pair. They do satisfy special commutation properties with a semigroup which is extremely important on the Hardy space, which is called the Lax-Berling semigroup, and which is just the semigroup of Galilean transformations. So you just multiply a function f by the character e to the I eta x, and in order to save the fact that f belongs to L2 plus, so the fact that the Fourier transform is supported in Xi non-negative, you need to impose that the parameter eta is non-negative. So that's why it's a semigroup and not a group. And we shall prove that these special commutation properties of the operator L and B on the one side with the Lax-Berling semigroup on the other side, so of the equation and its integrable structure on the one side, and the structure of the Hardy space lead to an explicit formula. And it leads this explicit formula completely bypassing the inverse spectral theory. So that would, in some sense, the main message of the talk. And the typical example is, in fact, the Benjamin-Ono equation, which is also an equation that can be handled by the method of commuting flows that Monica discussed in her talk. But here I'm going to talk about this equation from the viewpoint of finding an explicit formula, a simple explicit formula. Okay, so what is the plan of the talk? I'm going to talk about, in fact, 3 different equations, which to some extent have this structure of being integrable and having these commutation properties with the Hardy space structure. The first one is the Benjamin-Ono equation, but the 2 others are less known. The second one is the half-wave maps equation. It's a geometric equation. So the unknown is a function valued in the unit sphere in R3. And the third one is the Calogero-Moser derivative nonlinear Schrödinger equation, which is not the DNLS equation that Monica mentioned, which is another equation where the unknown is valued in the Hardy space. The specificity of the last 2 equations, the second one, the half-wave maps, and the third one, the Calogero-Moser, is that besides being integrable, besides having an infinite number of conservation laws, it's very difficult to prove global existence, even for smooth data, precisely because the conservation laws that are in some sense offered by the Lax pair structure, these conservation laws are rather weak. So they do not control high regularity of the solution. And this is a specificity of these 2 equations. This is not the case of Benjamin-Ono. For Benjamin-Ono, the collection of conservation laws is sufficiently strong to ensure global existence for, say, smooth enough solutions. So I'm not going to talk about low regularity solutions, unlike in the talk by Monica. I'm rather going to focus on smooth enough solutions, not too much decaying, but at least in some Sobolev space, let's say H2. But I'm going to try to understand how to describe the solution itself and how to get an explicit formula, and then how to deduce from this explicit formula a number of properties of the solution, in particular, not only the question of global well-posedness for the last 2 equations, but also the question of long-time behaviors or asymptotic behaviors with respect to various parameters. So this is the plan of this talk. Okay, so the Benjamin-Ono equation is this one. So it was introduced again the same year that as Gardner, Green, Kruskal, and Miura found this beautiful structure of KdV in 1967 by Benjamin and other people, by Davis and Akrivos, and then by the Japan physicist Ono in 1975. So again, I write it down here. You will notice that this is a pseudo-differential equation in the sense that the operator absolute value of dx here is a Fourier multiplier, which is not a differential operator. So if you prefer, with the notation of Monica, absolute value of dx is just the composition of dx with the Hilbert transform H, okay? So I prefer to write it down that way because sometimes the Hilbert transform has different definitions according to the authors. So there was a rigorous derivation from the Euler model by Bonal and so it's an equation for fluid mechanics. I will not discuss this too much. And I will remind you this global well-posedness of the initial value problem in the sense defined by Monica Vision, not analytically, but only continuously well-posed, starting with Jean-Claude Sau in 1979 and finishing with this beautiful result by Philippe, Lawrence, and Vision in April 2023, I think. So I will not discuss this log regularity again. I will focus on my sole solutions, so H2, but I would like to know more about these solutions. I would like really to describe them. So let me maybe discuss the Lax pair structure in more detail here. So again, I remind you the definition of the RD space L2 plus of R, which is this set of functions in L2 such that the Fourier transform is supported into the half-line xi non-negative. But that's also, thanks to a very famous theorem due to Pele and Wiener, the set of holomorphic function in the upper half plane C plus, corresponding to imaginary of Z, strictly positive, corresponding to these holomorphic functions such that the L2 norms on the horizontal lines of these functions are uniformly bounded. Okay. So in particular, these guys have a limit as y tends to 0 plus, f of x plus iy as a limit in L2 of R, and this limit is precisely the function on L2 of R. So there is this these two definitions that we will use a lot. Extension, a function on L2 of the line, extended to a holomorphic function on the upper half plane. This closed subspace of L2 is, of course, equipped with an orthogonal projector, which is called the Rietzgau projector, and which just in Fourier representation corresponds to cut off the Fourier transform, the value of the Fourier transform of the half line. And what is really important in all this story are some special operators that are called Toeplitz operator, that were introduced by Otto Toeplitz in the early 20th century. And these Toeplitz operators are, in some sense, ersatz of multiplications, except that the function b in L infinity acts on L2 by multiplication, but not on L2 plus. So in order to define an operator on L2 plus, I have to project the product BF through this Rietzgau projector. And this is a nice bounded operator on L2 plus. And now I introduce my two partners of the Lax pair. So the first one is an operator, an unbounded operator or bounded operator from H1 intersection L2 plus into L2 plus. If U is smooth enough, again, real valued in H2, this will be LU of F equals 1 over I df dx. So just the standard one derivative, was a first order derivative and made self-adjoint by this factor 1 over I, minus the Toeplitz operator of symbol U. Okay, so U, of course, in particular is in L infinity, so there is no definition, no problem of defining this guy. And if U is in H2, mod du will be in H1. And again, it's not a problem of defining BU on L2 plus. And you can prove that this BU is in fact a bounded operator on L2 plus, anti-self-adjoint. And it's also bounded from H1 plus into itself. So it's a very nice operator here. And so the result, which was proved in different versions by various authors, is that if I take a solution of a sufficiently smooth solution, let's say H2, of my Benjamin-Ono equation, then the derivative, we have this Lax pair identity, the derivative of LU with respect to time equals the commutator BU LU, if you prefer, BU-LU minus LU-BU. And this is really the crucial. So it's just a calculation. The problem is not to make the calculation. The problem is to find the good guys for which this calculation makes sense and is correct. And this is, of course, not easy at all. And as a consequence, and as was, in fact, also recalled by Monica Vision in her talk, if you define the family of unitary operator by this linear ODE, here it's really a linear ODE because remember that BU is time-dependent, continuous, valued in anti-self-adjoint bounded operators on my Hilbert space. So it's just a linear ODE on the space of linear operator on a Hilbert space. And then you get, of course, unitary operator because BU is anti-self-adjoint, and you get the formula that Monica also mentioned and emphasized, that at time t, my lax operator is unitarily equivalent to the lax operator at time t equals 0 through the conjugation by these unitary operators U of t. So far, I might give you the impression that I'm repeating part of the previous talks. Now I'm going to change a little bit because I'm going to write my formula. So the explicit formula, again, I give the other definition of this Lax-Burling semigroup, which can be seen as a semigroup of Toeplitz operators, in fact, for eta non-negative. And if you look at the infinitesimal generator of this semigroup, you will get the multiplication by x. And the multiplication by x, unlike the case of L2 of R, this multiplication is no more self-adjoint. Of course, it's not bounded, but it's not self-adjoint either. So we are going to introduce the adjoint of capital X that I will call G. For G, because of generator, it will be the generator of the adjoint semigroup, the right Lax-Burling semigroup, the adjoint Lax-Burling semigroup, which is here, S of eta star equals e to the minus I eta G. And this generator is very easy to describe in terms of, again, Fourier representation. The domain of G is just those functions in L2 plus in the Hardy space, such that if I look at the Fourier transform and I restrict it to the open interval when it's supported, this Fourier transform is in H1 of this open interval. And in that case, the Fourier transform of the image of F by my operator G is just the derivative, the derivative of the Fourier transform, which is, of course, conveniently extended by 0 outside of 0 infinity. So this is my object, in fact, the crucial object that I will use during the whole talk. And this is this operator G equal X star. Now, I will also define some linear form on the domain of G, and in fact, on more general functions, which is I plus of F, which is the right limit of the Fourier transform at 0. Okay, so if, of course, this Fourier transform is right continuous at 0, which is, for instance, the case of functions which are in the domain of G. So why do I call it I plus? Because if you, in some sense, well, you know that for Fourier transforms, in general, the value of the Fourier transform at c equals 0 is the integral of f. Here, it's not an integral. It's some kind of semi-integral. And the very interesting thing is that you can define it even if f is not integrable. Okay. There are plenty of functions which are in the domain of G. For instance, there is a function which is extremely important for Benjamin Ono, which is related to the soliton of Benjamin Ono, which is 1 over x plus I. 1 over x plus I is definitely not in L1 of R, but it's in the domain of G, and so you can define it's I plus, for instance. So the theorem that I proved a year ago is that if I take a real solution of the Benjamin Ono equation with data U0, then I can describe completely U by means of the projection, the Riesz-Zegge projector. Remember, so U is a function of X, it's on L2 in particular, so I can project it in L2 plus, and the projection is called pi U, of course, and then I claim that U is pi U plus pi U bar just because U is real valued. This is true for every real valued function. But now, for this solution of the Benjamin-Ono equation, I can give a formula for the value of pi U in the upper half plane. So what is this formula? Let me read it calmly. So I take a Z in the upper half plane, Z in C plus, and I compute pi U at time t and at this point Z in the upper half plane. And I get that this is 1 over 2i pi I plus, remember I plus was defined here, of the following function, which is the action of pi U0 on pi U0 of this resolvent. You take G minus 2t LU0. Remember, LU0 is the Lax operator associated to the initial data, minus Z identity. You can prove that this resolvent is well defined because you can prove that G minus 2t LU0 is what is called maximally dissipative operator. If you refer it to, for instance, the theory of Ile-Yoshida semigroup. And so you have this formula. And this is always true for every H2 solution. So now what I'm going to discuss briefly is the proof of that. So of course, I will not give you the whole proof. I just want to give you a flavor of this, just to show you that this is really something independent of spectral theory, but it's not independent of the, of course, of the Lax pair structure. So first of all, as I told you, U is the sum of pi U and pi U bar on the real line. There is no difficulty. It's just because U is real value. And now I start from a version of the inverse Fourier transform formula applied to every function in the RD space. So I claim that for every function in the RD space, if I pick a point in the upper half plane, Z, then f of Z is nothing but 1 over 2i pi I plus of G minus Z identity. So you just take the resolvent of G acting on F. Okay. And another way of writing this is writing the I plus is to take the inner product of this resolvent with the function e to 1 over 1 minus I epsilon x and take epsilon go to 0 plus. It turns out that 1 over 1 minus I epsilon x is in the RD space. It's easy to check. And when you take the limit, you always obtain the I plus. So this is not difficult. It's really a reformulation of the inverse Fourier transform, okay, using this operator G. And now I apply this to my unknown function, pi u of t, which is precisely in L2 plus. And I apply, I look at in the right-hand side, I see an inner product on L2 plus, but I have unitary operators acting on this inner product. So what I'm going to do, sorry, it seems that you don't see me. Oh, I'm so sorry. Yeah. What I'm going to do is to apply the unitary operator U of t star to both sides of this inner product. And then I get to something which may seem a little bit complicated. Pu at tz for every z in the upper half plane is the limit as epsilon tends to 0 plus of, well, there are essentially three terms. First term is the resolvent of u star g u. Second term is the vector u star acting on pu. And third term in the right-hand side of the inner product is u of t star acting on 1 over 1 minus I epsilon x. Now, I claim that it's possible to compute both of these three terms in terms of the time t and the initial datum U0. How? Well, we need for that to use some crucial identities. And these crucial identities are summarized in this lemma that you can see. The first lemma tells you that if you take, in fact, it's a reformulation of the Benjamin-Ono equation here. dt minus bu of pu is I Lu square acting on pu. You can prove that it's completely equivalent to the Benjamin-Ono equation when you write it down as pu, for pu, okay? The second point is that the action of bu on this magical function approximation of 1 minus I epsilon x to the minus 1, is the same as the action of minus Lu square on the same function, plus something which is small in, say, L2, as epsilon goes to 0. And the last, but not least important commutation identity is that the commutator of G and Bu is related to the commutator of G with Lu square, and there is also a linear term here, minus 2Lu. So I'm not going to prove these identities, or they take some time, but it's not difficult, again. And then I claim that if you use these three identities, you get the following identities for the three terms which arise in this complicated inner product of the previous slide. For instance, U of t star acting on Pu is e to the it Lu0 square acting on Pu0. This is only in terms of U0 and t. Why? Well, just take the derivative. The derivative of this will give you two terms. There will be a first term, which is U of t star acting on dt Pu, and the second term, because U of t is solution of some ODE, will give you minus U of t star Bu. So you apply the first identity, and then you get I Lu square acting on Pu, but you have U of t star, and U of t star Lu gives you Lu0 U of t star. You do it twice, and you get immediately this formula. And you could do the same thing for the other lines, and using these identities and plugging them in this complicated limit here, you obtain the formula which is the explicit formula in my theorem. Okay, I'm perfectly aware of the fact that just a flavor, but I just wanted to make sure that you understand that essentially the main tools are a complete use of the Lax pair structure, and in particular, a use of the structure of Bu. Sometimes we talk about Lax, but we forget about Peter. Okay, here Peter has a very crucial importance. This Bu is absolutely crucial. Okay, now let me give you just one application of this that I discussed in some other talks last week. I think that some of you were there. So it's about the zero dispersion limit of the Benjamin-Ono equation. So we are not interested in finding existence of solution of some PDE, but we are rather interested in looking at the behavior of this Benjamin-Ono equation when the dispersion operator is affected with a small parameter epsilon going to 0. Then it's absolutely non-trivial to even for small and for initial data which are smooth, it's absolutely non-trivial to understand what would be the solution at the limit. First of all, there will be probably limits because the L2 norm is conserved. It's one of the conservation laws of the Benjamin-Ono equation. So we have a family for all time. The solution U of epsilon of t is a family of L2 which is bounded. But okay, apart from this, what would be the solution? The solution formally should be the solution of this inviscid Burgers equation, dtu plus dxu square. But we know that this develops very strong singularities. And in general, this implies very big oscillations, as was observed by numerical simulations. So what we can prove, in fact, in the whole generality, is that this is weakly convergent in L2 to the unique solution of this problem. So ddx, so zd of u0 is for zero dispersion of U0 for initial data U0 of Tx, and you have just this measure here, 1/2 time of the measure 1 minus some measure mu, which is easily computed in terms of the initial data U0. So this is not the first attempt of proving zero dispersion limit. There is a very long story about zero dispersion limit, in particular for the KdV equation and the famous and seminal results by Lax and Livermore. But unlike Lax and Livermore, I don't use inverse spectral theory here. I just use my explicit formula, and I get this very general formula. Another possible application is more than a perspective. In that case, there is the problem of long time behavior. One of the important results and problems about solution in dispersive equations is to describe the long time behavior of solutions. You can ask the problem for KdV. You can also ask it for Benjamin-Ono equation. And for the moment, it's a completely open problem. This is called the soliton resolution conjecture, which tells you that as t goes to infinity, the solution of Benjamin-Ono will be a sum of solitons, in some sense, plus something which is dispersive, for which you have some kind of scattering theory. Okay, so we are currently working with Elliot Blackstone, Louis Gassot, and Peter Miller on this conjecture. And of course, a central role will be played by our explicit formula. So let me pass to the second example. I will be a little more sketchy, of course, on the second of the second and the third examples. But so for this second example, it's in fact an even simpler equation. It's just some kind of, if you know a little bit of Landau-Lifshitz equation, which is a limit of Heisenberg's spin chains with interactions with the nearest neighbors. Here you have a 1/x² interaction. And if you pass to the continuous limit to that, you get this nice equation, dTs equals S wedge mod ds. So S is a function valued in the unit sphere of R3, S2. And so you should think of S as a function, a vector function valued in S3, in R3, and the mod D operator is always the same in X, okay? And so you have two functions valued in R3, and you take the wedge product, okay? So this is, you can prove that it's a quasi-linear hyperbolic system. And as such, you can prove local well-posedness of the initial value problem. In this space, of course, it's not HS because the function being in S2, it has to have some background at infinity, which is a constant on the point on the sphere, plus some remainder term would be in HS, valued in R3, for S big enough, let's say bigger than half the dimension plus 1, which is here 3/2. And so you can prove local well-posedness. You can also prove energy functional, in the sense that this quantity, which is the homogeneous H1/2 norm, if you prefer, of S, you can write it down also that way, is a conserved quantity. The problem is that this is essentially the strongest conserved quantity that you can have here. So unlike the examples that we had on KdV in the talk by Monica Vision, and on the first part of my talk for Benjamin-Ono, where I told you that the global existence of smooth solution is not a problem because we have many conservation laws controlling essentially all the Sobolev norms, as for KdV and this Lax result proved by that was recalled by Monica. Here we are lacking conservation laws controlling high Sobolev norms. And so proving global existence in such a situation is really a challenge. So even if there are Lax pairs that I'm going to tell you now, these Lax pairs are not strong enough to give us enough conservation laws and control of the solution. So for the Lax pair are the following. So you can reformulate this equation, replacing your function valued in the sphere, by a function valued in the 2x2 matrices, which are Hermitian and involutive, U square equals identity. And in that case, you get the following nice equation, which is a lax pair identity in itself. It tells you that the dt of U is minus I over 2, the commutator in C2 in the 2x2 matrices of U and of mod dxu. Again, this mod dxu, which is everywhere here. Okay, so as a consequence, we have, in fact, a collection of lax pairs. In fact, we have two kinds of lax pairs. First of all, what is the auxiliary Hilbert space? I'm going to work with spinors because my unknown function is a function which is matrix valued. So my Hilbert space will be the space of vector valued functions, spinors valued in C2. Again, I will use the Hilbert transform H, which I define like this. And I introduce the action of U on the spinors just by multiplication matrix on vector. Okay, so this sends, of course, L2 into L2. And then I form the following operators. The first one is the commutator of the Hilbert transform with this multiplication operator. And the second one is a little more complicated. This is Peter. And this one is minus I over 2 mu u mod dx plus dx mu u minus mu mod dxu. And then comes the two results. The first one is that dtt of Lu is bu Lu. Again, that's the same formula, the lax formula with capital U now. But there is also an equation when you replace L by T, where remember, this is a Toeplitz operator, so you can also define it. As soon as you work not on L2, but on L2 plus, so the closed subspace of L2, the RD space valued in C2, and in that case, you just have to sandwich your B operator, so you sandwich Peter between two Zeger, okay? And you get that. So what is really important here is that the structure of these operators, lax operators, they are very different from what we know in KDV, in the case of KDV, or in the case of Benjamin Ono. They are, in some sense, very bounded operators. They are low. This TU is just of operator of order 0. This one is even of a negative order in some sense, as in fact, it's what is called a Hankel operator, and you can prove that it's exactly a Hilbert-Schmidt operator if we are on the energy space. So for U finite energy, the famous H-half energy that I introduced in the beginning correspond to Hankel, to lax operator, which are Hilbert-Schmidt. Okay. But still, there is a classical result by Kronecker about Hankel operators, which tells you that a function U is rational, a rational function of the variable X, if and only if this operator Lu, this Hankel operator, is finite rank. And this implies something very nice. It tells you that for this equation, this half-wave maps equation, if the initial datum is rational with some denominator of given degree, then so is the solution for all time, well, as far as it exists, of course, which is somewhat magical. So some people were not completely convinced, so they made what they call the Polensatz. These are physicists from KTH in Stockholm. In 2020, they plugged a rational expression in the equation, and they found a very nice system of ODE, which is not so nice. In fact, it's a little bit complicated, but it's an ODE system of Calogero-Moser type. Well, I don't have time to discuss that. That's also why we called it the Calogero-Moser DNS. This is in fact related to a family of Calogero-Moser type integrable equations. I will talk about another one in a minute. But nevertheless, the problem is, again, that we don't have enough conservation laws to control my solutions unless, though we have two lax pairs. So the solution, again, will be in the explicit formula. And you can prove that, again, if I write my solution as a background at infinity plus something in H2, that the solution will be given, and at least the deviation of the solution from the background at infinity is given through its projection, its Zego projector in the upper half plane, by a formula which is completely similar to what we found for Benjamin-Ono, except that here your L is replaced by T, a Toeplitz operator, which is a bounded, very nice operator. And using this explicit formula, we can prove that at least if the initial datum is rational, the solution is global. So we don't use any kind of conservation law. We just prove that this operator here can be, in fact, made acting on a finite dimensional space on which everything works and which includes, of course, the initial datum. And on this finite dimensional space, you can prove that this matrix is always inversible, even if Z is real. Not only if Z is in the upper half plane, but if Z is real. So it's a question of eigenvalue. So you can prove in some sense that there is the real line is not an eigenvalue of such an operator. It's not completely trivial, but you know, it's very explicit way of doing that. Okay, just for the end, I think I have 5 minutes more. I would like to discuss the third example of equation, which is the Calogero-Moser derivative nonlinear Schrödinger equation. In that case, my equation really looks like a nonlinear Schrödinger equation, I dt plus dx squared u, but then the nonlinear term is somewhat weird, I would say, because I have this derivative part, which is non-local, d plus mod d, acting on mod u squared, and the whole is multiplied by u. And what is really important is that we are going to assume that u is valued in some Sobolev space, no problem, S big enough, but also in the RD space. Why? Because observe that if u here is in the RD space, the guy here is always in the RD space because d plus mod d is valued in the range of pi. So this guy is automatically in the RD space. Now, if the functions are smooth enough, the product of two guys in the RD space is still in the RD space. So you can prove that, at least formally, this equation preserves the RD space target. Okay. So it was introduced by other physicists, Abanov, Bettelheim, and Wigman. And again, they are dealing with Calogero-Moser systems of classical particles. So the same kind of Calogero-Moser systems found by the previous physicist in the previous equation. But you take a continuous limit in that case, and you get making some kind of Madlung transform. You get this equation. Again, you can prove local well-posedness in a sufficiently smooth Sobolev space, but again, the problem is global solution. Now, in fact, the situation is slightly different. You have plenty of nice conservation laws which are not that far for controlling high Sobolev norms, except that we need a little of what Monica Vision called equicontinuity in L2. Okay, as soon as you have equicontinuity, exactly as for D and LS, we will have global existence. So for the moment, we are not able to prove it, except in a special case, and this is in fact the content of my last theorem. I claim that, first of all, I have a Lax pair again. If I have a solution of this equation, then again, I have a Lax pair identity. But in that case, my operator LU is capital D. So again, capital D is 1 over I ddx, just as for Benjamin-Ono, except that unlike Benjamin-Ono, the Toeplitz operator TU is replaced by the product of Toeplitz TU and TU bar. The B operator is more complicated. I will not discuss that, but there is one. And again, it's bounded and anti-self-adjoint again. And I have, again, a formula of that kind for this RD space solution for every z in the upper half plane. So, okay. And really, if you want to prove this, you can follow the same scheme that I did for Benjamin Ono. You will get the same, exactly the same proof. You get that. Now, what is interesting is the consequence and the application. And the application is about n-soliton potentials. So I'm given an integer n, which is at least 1, and I'm given a function u, say, in H2, smooth enough. And the following properties are equivalent, and they are preserved by these dynamics. The first property is a spectral property about the operator LU. So LU is a self-adjoint, unbounded operator on my RD space. And I demand that the sum of the eigenspaces, you can prove that, in fact, there are only finite number of eigenvalues. You can prove that the sum, and you demand that the sum of these eigenspaces is invariant by the Lax-Burling, the adjoint Lax-Burling semigroup, and is n-dimensional, and it contains U. Okay, so this is it's a completely spectral property that you can prove easily is preserved by the dynamics. And the second property, which is equivalent to this one, is that U is a rational function of a certain type. So again, I will find rational functions, and these rational functions correspond, in fact, to a spectral property of the Lax operator. So typically, these are rational functions that we call n-solitons. They exist for all n. And for n equals 1, here's one soliton, which is in fact a stationary wave in that case, square root of 2 divided by x plus I. Now, this is the proposition. Now, my last theorem is in fact the following one. I claim that every n-soliton solution is globally defined in time. Again, you can write, if you want, an ODE system, but it's a terrible thing, okay? An ODE system for these n-soliton solutions in terms of the poles and in terms of the residue at these poles, assuming the poles are simple for simplicity. But it's really a nightmare, in fact, for proving global existence. Though, in fact, what we prove is, again, the global existence comes from this explicit formula, using, again, the fact that we can reduce yourself to a finite dimensional space here, and then you have a matrix. You just have to prove that this matrix has no real eigenvalue, and this can be done. So the second thing I would like to emphasize, and this is something that surprised us very much, is that as soon as we have more than one soliton, if n is at least 2, then for every regularity S, the Hs norm of U of t goes to infinity as t goes to infinity. It goes to infinity like t to the 2s. So what does that mean? It means that when I told you we cannot find conservation laws which control high regularity Sobolev, I was right. Because precisely here, I have something which is in all Sobolev spaces, but the solution is not bounded in any Sobolev spaces. And this is also a flavor of integrable systems, very different from KDV or DNLS. But I think it's a flavor which is also quite interesting to study. And of course, there is some work in progress proving that we have, in fact, global well-posedness for arbitrary data in L2+. And the question of long-time behavior is, of course, quite interesting too. Thank you very much for your attention.
Thank you so much, Professor Patrick Gerard, for your excellent talk. Question.
Toru.
Toru Osawa.
Hi, Toru. How are you?
Do you question or commentary?
Professor Osawa has a question. Professor Osawa, could you unmute yourself, please?
Yes. I can't hear you. In fact,
I'm sorry. I just applause your lecture.
oh, thank you very much, Toru.
Very, very beautiful.
Thank you. It means a lot to me. Thank you very much.
Are there any question?
I think Monica has.
May I ask a question? So let's go back to the Benjamin Ono equation and the explicit formula that you have. Okay.
Yes.
So right now, there is not even a conjecture for what radiation would look like, right? If you look at the soliton resolution conjecture, if you look at the part that doesn't contain a soliton, just the radiation, what exactly should that radiation look like? Can you use your explicit formula in order to give a prediction for what? So we know that the power in Benjamin Ono is not big enough to give us, true scattering, right? It's going to have some modified scattering behavior. Can you read it from your explicit formula?
Yes, at least in some special cases. That's what we are currently doing with my collaborators. And the special cases are rational functions. Again, rational functions are extremely important in all this stuff. So if you pick a function which is a constant time a soliton, so it's not a soliton, but you take a minus a soliton, for instance, minus 1 over 1 plus x squared or constant, then you can compute everything. And you will see some kind of scattering theory. But for the moment, I don't want to describe it too much because we are just working on some special cases. So it's a little too early to give you a general insight. But I just want to tell you that it's possible to make this computation thanks to this identity. Yes.
For rational functions.
At least for rational functions.
So could you also write down a meaningful formula for rational functions to Calogero-Moser? Can you just plug in, let's say, constant over x plus I?
Now, for Calogero-Moser, we can do it for not for all rational functions, but only for n solitons, okay? But for general rational functions, it's more complicated. We hope very much it's possible, but we have not tried. I agree with you, it should be of the same kind. We should be able to have, for instance, start with again, you take a constant time, the solitary wave, constant divided by x plus I. There should be the same kind of formula. For the moment, we have not succeeded in giving a general description, but I hope very much that it should be exactly the same. So there is some strong hope that at least for special rational data, we can really describe the long time behavior. Yeah.
Thank you.
More questions?
I think maybe I should look at the chat. I've not looked. Okay, thank you very much. Thank you. Okay,
Thank
good.
you very much, Professor Patrick Gerard, for your amazing talk.
Thanks a lot.
Yes. Okay. Okay. Thank you very much, Professor Gerard. Thank you, Professor Juan Limaco, for sharing this session. So we will have 1 hour break, and then we will connect with the talk of Professor Michael Ruchansky to this PDE day. So he will talk about very weak solutions. So all of you are invited to attend this talk. So thank you very much. Thank you.
Thank you very much. Bye-bye.
Hi.
Hello, Dr. Harris.
Hi, Professor Michael.
Okay. Hello, Professor Ruchansky. Hello, can you hear me? Okay. Can you unmute yourself?
Yes, hello. Yes, I unmuted. So let me just open. Okay, this one is the file. No. So just a second. So share. Can you see the file?
Yes, Professor.
Wait, I will now, just a second, I will move it here.
Okay.
So just this. Can you see it? No, 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 maybe not now. Wait a second to put. No, wait a second. Yes, so, no, can you,
Yes,
but
we
wait,
can.
it's strange because it's somehow, I don't see it now. You can see it, but wait, it somehow disappeared.
Mhm.
No, what's something strange going on? Because it changed to another screen. Oh. Ah, yes, can you see it now?
We can see. We can see. It's not in the. It's not in your complete screen.
It's full screen, should be full
Is-
screen.
It's not full screen. It's not full screen yet.
No,
No.
how do I resume, stop, okay, let me start. Like this, close this. Like this, okay, and then do reader. Can you see it
Very
now?
well.
Is it
Yes, I
full-
can see in full
full-
screen.
Full
Yes.
screen.
Can you
Okay.
try to move the slides?
Yes.
Very good. Perfect.
Okay, good. Thank you.
Okay, so maybe then we can start. So it's my big pleasure to introduce our next speaker, who is Professor Michael Ruchansky. Until 2018, he was full professor at Imperial College of London. And currently, he's a senior full professor at Kent University and a professor of mathematics at the Queen Mary University of London. Professor Michael Ruchansky does research in the idea of partial differential equations, and today we'll give a talk about very weak solutions to evolution equations. So, Professor Ruchansky, please let's start.
Yes, thank you, Jovan. Just to check how much time is the talk?
50 minutes. You can take 50 minutes.
Okay. Okay, thank you. So, okay, thank you. So first of all, it's a pleasure for me to give a talk at this conference. I see it's a very good conference with many interesting talks. So, of course, I'm also happy to give my lecture here, and I will talk about the topic of very big solutions to evolution equations. So to present you, to explain what is the main idea of behind very big solutions and how it can be applied to different situations. So basically, the main. Do you see the next slide now? So I changed the slide, so I hope you see it.
Yes, we see your next slide, Professor.
Okay, so the motivation behind this, so there have been talks already this morning, and when we saw that low regularity of data causes problems for nonlinear equations, but here we have also a similar phenomenon, although I will speak about linear equations in my talk, that low regularity in coefficients also cause problems. So let's consider a very singular PDE, like I wrote here, wave equation, but suppose that propagation speed, so it's a strictly hyperbolic equation, if we may say, but propagation speed here is very irregular. There is a delta function at time equals to 1. And then the question is how to interpret this equation. So one problem here is that if we cannot, unfortunately, work in the framework of distributions because let's say U is a distribution and then we would have to multiply it by delta function. And there is a famous Schwarz impossibility result, which tells us that we cannot multiply distributions. So if you would assume that product of distributions is another distribution, then quickly we would get a contradiction. So the question is how to understand this equation, also how to interpret solutions of this equation, and how to interpret well-posedness of this equation, because well-posedness would be existence of solution, uniqueness, and some kind of continuous dependence on the data in the sense of Adamar. So this is the main aim of this talk. And first, I give some I give some references and also start with the philosophical discussion. What could be considered to be solutions to such equation? So the notion of very weak solutions that I will talk about has been introduced in this paper 2015 with Claudia Garetta, who was a postdoc of mine at the time, where we proposed this notion for wave type equations, and then in subsequent works we applied this notion to different questions. For example, wave equations with not when we don't have Laplacian but we have Landau Hamiltonian. I will talk about this in more detail. This is when we have singularity in the electromagnetic field. Then acoustic problems, where we actually have singularity which is stronger than delta function, because we have to divide delta function by Heaviside function, which is even more impossible than multiplying distributions. And then a little bit more general, like operators with discrete spectrum. And then also we moved to equations on the Heisenberg group, where we consider subelliptic or hyperelliptic operators. So these are applications, some applications of this. And then more recent. And now it doesn't change the slide. Wait a minute. Yes, so it also has links with numerics, because we know that when we do numerical simulations for hyperbolic equations, it's kind of complicated, because we think of if you think of solutions being oscillatory integrals, there are oscillations, and these are hard to treat numerically, especially in higher dimensions. It becomes very consuming for the computer. So then there are some works here that I mentioned that we have analyzed some numerical aspects like parallel computing for such equations, implementing the methods of very weak solutions. I will show you some pictures later on. And then equations before which I mentioned, they were singularities with in time, but then one can also look singularities in X. So there are here a few papers dealing with X-dependent coefficients, and also with hyperelliptic versions of these equations. So we considered wave equations, Klein-Gordon heat equation, Schrödinger equation with singularities, and also one can apply it. So here is a recent paper, should appear next year, is when we consider discrete heat equation with singularities in conductivity and distributional data. Also, this kind of equation, when we consider strong singularity for the Sturm-Liouville problem, another recent paper where potential Q is can be also assumed to be a distribution, or even well, delta function or stronger. So this is to show, this reference is to show that this is a subject in development. So there are works on this, and there are a lot of open problems, as you will see when I present you this notion. It's a very open field where basically very little is known. So okay, so be more precise, so let's consider an example, simple example, wave equation, where we put a Heaviside function h here, we put delta here. So Heaviside function is here jumping from 1 to 2. So it's a singular discontinuity. And here the another coefficient is even stronger. Stronger singularity is a delta function. And there are basic questions is how to interpret this equation when you use a distribution. This is one question. And as I mentioned, Schwarz impossibility result says that in general, we cannot multiply distributions. We can sometimes do it when there is a condition on wavefront sets, like the one by Hermander. But then basically, if we have delta, then the wave front set is the whole space. So then these results are not applied. So it's a problem. And also, what is the right notion of well-posedness? So how to interpret the equation and how to interpret well-posedness of this equation. So these are a problem is that if you talk about weak solutions, we need always some integrability. And so here, weak solutions would not be working, soberly weak solutions, because delta is not locally integrable. So, okay, so let's consider, let me talk a little bit about an even simpler equation, which I wrote here, wave equation with propagation speed a of t. And we can even assume that a is strictly positive, so that we are in a simpler, strictly hyperbolic setting. So there are different approaches, and a classical approach is when a is C1. Then we can talk about classical solutions or distributional solutions, depending how regular the Cauchy data is. If the Cauchy data is regular, then we talk about classical solution, which means that solution U is a function, and we just plug it into the equation, and we want the equation to be satisfied pointwise. So this is a let's say we look for a smooth solution, or C2 solution, because we differentiate here twice. But already, if A is Herder of order alpha between 0 and 1, then I will show you this equation, this very simple equation may not have distributional solution. So we can find strictly positive A, which is also which is Herder, but then there is no solution in the space of smooth functions and no solution in the space of distributions, even for smooth data. So this still can be solved by resolved by looking at Gevrey data, or by looking at the ultra-distributional solution. So space of ultra-distributions is a bit bigger than space of distributions. So if A is locally integrable, then those approaches don't work, but then we can still look for solution in the space of hyperfunctions. So if A is measurable, then it's less regularity, and then there is a Kato theory of semigroups, which can give us a notion of solution. But here our question is A is a distribution. So A is a distribution, and then our question is how to deal with this equation. And I should mention that there is a Colombo approach to these equations, because Colombo theory allows us to multiply distributions on one hand, but on the other hand, there are problems with consistency. So if we want a notion, we want to find solution which is consistent with stronger solutions. So if there's a classical solution, we want our solution to be consistent with that. And this is not always achieved in the Colombo theory. So also in the Colombo theory, we need to have an algebra, and I will give examples where obviously we will not have algebra, so we will not have a notion of Colombo solution. So what this is a philosophical question. What is a solution? And a notion of solution, a good notion of solution, should be on one hand weak enough so that we guarantee that solutions exist. So if we say that we are looking for solutions which have to be locally integrable, then we rule out distributions. If we look for distributions, then solution may not exist because it may exist in the space of ultra distribution. So the notion, good notion of solution should be weak enough to guarantee existence of solutions. But on the other hand, it should be strong enough to give uniqueness and also to give consistency with more regular solutions if they exist. So we can say like any function is a solution by definition, then we have existence, but then we don't have uniqueness because it's any function, and then also we don't have consistency because we cannot recover if any function is a solution according to our definition, then we cannot recover smooth solutions if they exist. So we have to achieve this kind of balance between notion which is weak enough for existence, but also strong enough for uniqueness and consistency. So next slide. Doesn't go to the next page. Let's see. Something is slow with my computer. I think I missed a slide. No. Okay, so I have some problem with my computer, but I don't want to restart it, obviously, so there will be some delay. So Landau Hamiltonian, another motivating example. So we have, coming from physics, we have electromagnetic field. And so here we have Hamiltonian H0, where Q corresponds to electric potential, A corresponds to magnetic potential. And we can, okay, first half of the slide is some physical background, but mathematically, if we put all physical constants equal to 1, then we get this H plus Q, which is given in this form. So B is magnetic field, Q is electric potential. And let us consider wave equation for this Landau. So this is called Landau Hamiltonian, and let's consider wave equation. But for example, Q of T, electric potential, let's take dependent on time. And also there may be additional coefficient A of T here. And again, so this is a problem which we may want to study physically when the magnetic potential or electric potential has some jumps. So for example, here Q can be given like this. It means that we have two jumps. For example, if you switch on light, let's say, then electric current goes, so it's like a big jump. So there could be electric shock. So how to deal with this equation? Moreover, if A, for example, is like this, then we would have to multiply A and Q here, and the function T minus modulus of T minus 1 to the power alpha, we cannot multiply with delta. So the question is to deal with this equation. And another motivation will come in the next slide, which is, so this is Landau Hamiltonian case here in the first paper. And the second example comes from acoustics. Again, let's consider acoustic system, which I will, I formulate a system which comes from physics. And after some manipulations, in particular, X and T, if you switch X and T, then this is a technical trick. Then we get equation of this type, which is given in red here. And you see here B prime over B. And the physical meaning of B is a product rho C, which is a product of the density of the material and the wave speed of the material. And so B can be can have jumps, because natural assumption piecewise continuous function which is positive So let's say if it's an acoustic problem, so if I'm talking here in this in my office, and then the sound waves propagate and then they hit the wall, so the density of the air in the room is jumps to the density of the wall. So we have discontinuity of B. So if you think of B being Heaviside function, so piecewise constant function, then if it's a Heaviside function, if B is a Heaviside function, then B prime is a distribution, and so we would have to divide distribution. We would have to divide delta function by Heaviside function, and again, this is not possible at all in the sense of distributions. So it is a physically well motivated problem, but mathematically, again, the theory of distribution doesn't allow us to deal with this question. So next slide. So historically, maybe I before I give you the formulas for the definition, maybe some historically. Here you see pictures of Sobolev and Schwarz. So a notion of solution, as I mentioned a little bit before, classical solutions when we have solutions of functions which satisfy the equation pointwise, which we can do when everything is regular. Then we have Sobolev's weak solutions when things appearing functions locally integrable, then we formulate a notion of weak solution. Schwarz distributional solutions if objects are not locally integrable, like we have some delta functions, and we can talk about distributional solution when solution is interpreted as a functional. You may think what is the physical meaning of a solution which is a functional, but this is the way to do it. And so if we don't have distributional well-posedness, then we can talk about ultra-distributional well-posedness. And this paper of Colombini Spagnola and also the Giorgio Colombini Spagnola, they studied the equation which I gave before, very simple wave equation with the coefficient A of t, showing that we may have no distributional solution. And one thing to note about these notions is that they're backward compatible or consistent. We say consistent in a way that in the sense that if you have a distributional solution and it happens that we also have a classical solution, then we can recover classical solution from distribution, namely this will be a distribution associated to this classical solution. And if you have Sobolev weak solution and we have also classical solution, again, backward consistency means that if you have these two solutions, then they correspond to each other. We can recover the more regular one from the less regular one. So this is a crucial part that we will aim to achieve is this backward compatibility, that the notion that we introduce of very weak solutions is backward compatible. So if it happens that there is a more regular solution, then we can recover it from our very weak solution. Another maybe I have to apologize for too much philosophy in this talk, but another aspect to put this into perspective that if you think of what kinds of solutions there are maybe two different types in the classical literature. So a classical solution is a notion which, as I said, pointwise equation is satisfied pointwise. So this is the same notion for all equations. If I say that function is a solution if the equation is satisfied pointwise, I don't really care if equation is elliptic, hyperbolic, or anything else. It's a notion for all, which works for all equations. However, Sobolev weak solutions, it's very different. It depends on the equation. So if we look at papers where authors deal with weak solutions, there is always a definition saying that we call a weak solution of this equation something if a function if some integral equation is satisfied. So usually we rewrite equation in the integral form, and then we want this integral equation to be satisfied for a weak solution. And how we write equation in the integral form depends on the equation. So here a crucial point is that Sobolev weak solution, the notion depends on the equation. Then we move on, like distributional solutions. Again, we have a theory of distributions, and then we plug the distribution into the equation. We want it to be satisfied in the sense of distributions. So again, distributional solution does not depend on the equation. And our case, so again, Colombo theory, we have a Colombo algebra, we take an element, we plug it into the equation. So again, this notion does not depend on the equation, but here our very weak solutions. That's why we call them. Maybe it's not the best term, but we call them very weak solution to emphasize similarity with Sobolev weak solution, because it is adapted to the equation. So for each equation, I will give you now examples. For an equation, we have a notion of the notion of weak solution will be adapted to the particular equation, or rather to the properties of solutions of regularized equation. Okay, so now I give you some formulas, starting with a simple example, so which I already showed briefly. Let's consider wave equation, Cauchy problem for the wave equation, and A is non-negative, and we can even, for simplicity, assume that A is strictly positive, so we don't have to deal with multiplicities in this equation, so it's strictly hyperbolic in the classical sense. And here is a fact, which I summarize here, that if A is continuous and the data is smooth, then there may be no distributional solution. So this is a very striking, remarkable fact, which was I mentioned the paper by Colombini Spagnola, a few papers, where they showed this, I think, very, very remarkable fact that equation seems innocent, A is strictly positive, continuous, U0, U1 are smooth, compactly supported, but the solution U is not there is no solution in the space of distribution. So U of t is not a distribution for any positive t. So immediately, for small t, we jump out of the space of distribution. However, and this is crucial, if A is smooth, then there is a smooth solution. So if A is smooth, then we have very good solution, which is smooth. But if A is continuous, and I was giving you example of jumps, and I was giving you examples of delta functions. So you can imagine it's much more much stronger singularity already for continuous A. We may have this problem. So okay, so the idea is the following: we regularize A. So this is a natural idea. Friedrich's regularization. I say Friedrich's type because we will see that, as I mentioned, the notion of very weak solution will be adapted to the equation, and sometimes we have to regularize not with the usual Friedrich's regularization, but with a little bit different. So we put here omega of epsilon. So omega of epsilon goes to 0. The standard Friedrich's regularization would be when omega of epsilon is equal to epsilon. But here we may consider, for example, slower decay to 0, for example, logarithmic decay, which is slow, and then this is what will be required. And a definition is that if we have a family of smooth functions, f epsilon, a family of smooth functions, it depends on epsilon, and we can say that it's moderate. So this is definition of a moderate family if its dependence on epsilon is bounded by epsilon to the power minus n for some n. So there exists n such that f epsilon as epsilon goes to 0 is bounded by epsilon to the power minus n. So the family may blow up as epsilon goes to 0, but it blows up in a moderate way. There is no super exponential, nor exponential blow up, but polynomial. And a simple observation here is that if you start with a distribution A, and to avoid some technicalities, let's consider compactly supported distribution, and we consider a family A epsilon, which is regularization of A with our Friedrichs modifier, then it's easy to show from the structure theory of distributions that A epsilon is moderate according to this definition. So in some sense, we can think of compactly supported distributions as moderate families of smooth functions. So of course, this is a well-known view at the point at the theory of distributions, that we can look at them as families, but the space of families is bigger. So every distribution can be corresponds to a family. Of course, this family is not unique because we have a choice of the Friedrichs modifier, but so every distribution can be viewed as a family, a moderate family, but not every moderate family will come from a distribution. So we have here enlarged the space. So the space of distributions we have enlarged to the space of moderate families of smooth functions. So it means that if we may not have it, if we are looking for solutions, then maybe we find and we cannot find a solution in the space of distributions. Maybe we will find the solution in this as a family of moderate family of functions, and that's exactly what we are going to do here. And so this is a definition of a very weak solution in this case. So what we let me explain first what's going on, and then I will explain the definition. So we will regularize A. So let's say A is distribution. We regularize it with that Friedrichs modifier. We get a family A epsilon, and so this A epsilon is smooth because we take a convolution with a smooth function, which is a Friedrichs modifier. So A epsilon is smooth. If A is strictly positive, then also for small epsilon, this function A epsilon is strictly positive. And then we're exactly in the situation as before. I mentioned that we have a wave equation with smooth and strictly positive coefficient A epsilon. Therefore, there exists always a solution U epsilon. So for each A epsilon, we get U epsilon as a solution to this the same equation with the same Cauchy data, but with A replaced by A epsilon. So this is how we construct A epsilon. And now this family A epsilon that we are obtaining this way, we will call this family a very weak solution of our Cauchy problem with singular coefficient if there exists a moderate regularization A epsilon of A such that the family U epsilon that solves this equation is moderate. So again, let me repeat, because this is important, that very weak solution is a family of smooth functions depending on epsilon, and it is a very weak solution, a family, if there exists a moderate regularization A epsilon of A such that the U epsilon solves this equation with A epsilon, and U epsilon as a family is moderate. So you may see that here, okay, we can regularize A in different ways, then we get different families of U epsilons. So we have to think what does it mean, this equation, this notion. But here is a summary of results. So first, existence. These are theorems, which I will not prove here, but I'm trying to explain the idea. So for each distribution A, the Cauchy problem with A has a very weak solution. So we have existence we have existence in the of very big solution. Uniqueness, this very big solution is unique in an appropriate sense, because we have to always, for uniqueness, we have to make sense, and uniqueness depends on the notion of uniqueness, because let's say two functions may be the same or not the same, depending how we measure the uniqueness. So if two functions may be equal to each other pointwise, they may be equal to each other almost everywhere, and functions which are equal to each other almost everywhere, they are not equal in the pointwise sense. So we have to define what is uniqueness, which I will do on the next slide. But so we have existence, uniqueness, and we have consistency, and consistency is written here. So if A is smooth, let's say A is smooth and the data are smooth, then we have a classical solution, as I said. But we also have a very big solution, which is a family. And so U epsilon is a family of a very big solution, which is a family corresponding to A epsilon. And here's the theorem is the following, that we recover, so this consistency, we recover the classical solution in the limit. So for any regularizing family A epsilon of A, U epsilon will converge to U in the strong sense of C infinity as epsilon goes to 0. So we have consistency. If it happens that we have, so we always have very big solution by the first theorem existence, but if it happens, we are in the situation when we also have classical solution, then we recover classical solution in the limit. If it happens that U0 and U1 are distributions, then so that there is distributional solution, then one line that didn't fit here in the slides, then basically what we have is that still U epsilon goes to U, but not in C infinity, but in the space of distributions. So in this case, we have distributional solution. Classical solution will be distributional solution, and then we still have U epsilon, a family of smooth functions, but U epsilon will converge to the distributional solution now in the space of distributions. So the existence, uniqueness, and consistency. Now I said that we have to define uniqueness, and we define it in the following way. So here I put first our Cauchy problem, and then CP, and then Cauchy problem epsilon with A epsilon. And what is uniqueness of very big solution? It is something which seems to be very natural here. It's basically the stability. And stability, it says the following, that if we regularize, so as we said, we can regularize A in different ways, because it may be, first of all, we have a choice of Friedrichs modifier. So, but if we regularize it in different ways, we get two regularizations, A epsilon and A epsilon tilde of the same A. Then we have solution families U epsilon and U epsilon tilde. And basically uniqueness means that if the difference between A epsilon and A epsilon tilde is negligible, then the difference between solution families U epsilon is also negligible. And here it's in formula, it says that if the difference between A epsilon tilde is bounded by epsilon to the power n for all n, then also the difference between U epsilon and U epsilon tilde is bounded by epsilon to the power n. So this is unique. This is the uniqueness. But I put the norm here, and this norm is something that depends on the where U epsilon is. So U epsilon, we can put L2 norm, we can put L infinity norm, and so on. So then we get obviously different things. But so if you put, and I will give you an example how we do it. But so uniqueness basically means stability. So it seems to be very quite natural, and with these notions of very big solutions and uniqueness, then we have existence, we have uniqueness / stability, and we have consistency. So here let me give you an example of that I mentioned before, Landau Hamiltonian, where we consider equation like this. And it is, so this also shows that, let's say, Colombo approach doesn't work. And this also shows what I said, that we have to, the notion of very weak solution depends very much on the equation. So here H is a Landau Hamiltonian given like this, and we will define this notion based on the spectral properties of the Landau Hamiltonian. So it's well known that the spectrum of the operator H is discrete. So eigenvalues are lambda k. They are known. They are called Landau levels. Also, and they are infinite dimensional. So eigenspaces are infinite dimensional. So we can define the Sobolev space HS adapted to H by the spectral theorem, and then theorem 1, which is a regular case. So we always start with a regular case because we want to define a notion of very weak solutions dependent on the properties of solutions of regularized problems. So here regularized problem is for example A and Q. These are functions which appear in the equation. Let's say the C1 or even the L infinity with derivative in L infinity, strictly positive. Then we consider, so we say that no, here if you take the data in the Sobolev spaces adapted to this H defined here, then we can prove that the equation has a unique solution in this space here. So the space is not regular Sobolev spaces. It's a Sobolev spaces adapted to the spectrum of the Landau Hamiltonian, but we have this regular property which we'll use now on the next slide in the definition, that if we have so if A and Q are regular, then and we have data in the space of in Sobolev spaces, then the solution is in the Sobolev spaces. So we can call this classical. We can call this classical solution. And here is a definition of very weak solution. Again, we will regularize. We regularize A epsilon. We can regularize Q epsilon, and according to the previous theorem, because we regularize them, they become even smooth. So they certainly C1. And then, according to this previous theorem, there exists U epsilon in the corresponding Sobolev space. So this U epsilon, which is with values in Sobolev space of order S, we say that it is a very weak solution of order S if there exist moderate regularizations A epsilon and Q epsilon of A and Q, such that the family U epsilon is moderate in this space, which means that we have this bound, we have this, again, moderateness is as I said, is polynomial blow up, the epsilon goes to 0. So if you have this property, so then this is a notion of very weak solution. And we have existence, so theorems that for any positive A and Q, for any data, the Cauchy problem has a very weak solution of ODS. It is unique in the sense of stability, which I described, and where I was putting norms there. I said that we have a choice of the norms. There we would put in the Sobolev norms. So according to that definition, it's unique. And also consistency. So if A and Q happen to be regular, then we have a classical solution, which is given by the previous theorem in the Sobolev spaces. And we have also very weak solution, and consistency means we can recover classical solution from the very weak solution. Namely, it means here that U epsilon converges to U in this space as epsilon goes to 0. So we have existence, we have uniqueness, and we have consistency. So the same here. So this is the situation which I described. It's actually acoustic system. This is actually echo effect, which I said I'm talking in the room, and then the sound waves hit the wall, which is maybe rock. So then we know the echo effect because the sound gets reflected, and it is described by this equation. And as I said, B has a jump, so it means we have in the space of distributions, we would have to divide delta function by Heaviside function, which is impossible. But as you will see, we avoid this, we somehow resolve this problem by this notion of very weak solution. We say that again, so what we do, we regularize B in a moderate way, we get B epsilon, which is positive. And then this solution, because B epsilon is regular, this equation has a solution, which is U epsilon, which is in the usual Sobolev space, HS. So then we can say that this family U epsilon is a very weak solution of order S if there exists a moderate regularization B epsilon of B, such that the family U epsilon that we get here is moderate, and moderateness here, as before, depends on the norm. So you see here we put Sobolev norm. So you saw that in example 1, I put here some L infinity type norm. In example 2, I put Sobolev space adapted to the spectral properties of the Landau Hamiltonian. Here I put the classical Sobolev space. So, and so according to this definition, we have the theory which says that for Sobolev data, the Cauchy problem of order S, the Cauchy problem has a very weak solution of order S. Sorry. It is unique in the sense which I showed before, where for the norm, for the uniqueness, in the definition of uniqueness, we take Sobolev norms, and we have consistency. So if B is C1 and U is in the Sobolev spaces, then we have a classical solution in the Sobolev space, and we have also very weak solution, which is a family. So the classical solution U and the very weak family U epsilon, and then U epsilon goes to U as epsilon goes to 0, and it does not matter how you regularize B epsilon. I mentioned that there is non-uniqueness in the way we regularize, so it doesn't matter how you regularize, we recover classical solution from this very weak solution. And we can do a few more things because so this is just definition, but we can do a few more things. So here I repeat this a little bit. I think I don't have so much time, so let me just say that yes, we can do a few things. So for example, we can prove some estimates like for example, we can prove this estimate for each B epsilon, U epsilon. We prove an estimate like this. And remember that B epsilon is regularization of B. So as epsilon goes to 0, then B is if B is good enough, because B, remember what B was piecewise continuous function. So it means that if it's piecewise continuous function, then B epsilon goes to B. So we get in the limit, we get this kind of estimate. And what it shows is that U epsilon has a uniform bound independent of epsilon. And what this implies that we can start taking some limits along subsequences, maybe in the weak topology, in the weak stat topology, and then we can talk about the limiting behavior as epsilon goes to 0, even if B is regular. So this kind of analysis we can do, and actually such analysis has been carried out in the paper by Jens Wirth and Mohammed Sibih, where they analyzed microlocal properties of this reflected solution based on this approach of very weak solutions, because in order to analyze any properties, in order to do any numerics, we have to have Wilposen's statement first, and then the very weak solutions give us such Wilposen statement, and then we can look at things like propagation of singularities, maybe at the propagation of wavefront sets, and so on. So we can start some more rigorous analysis. So let me show you a few examples. So I give you, because there are some interesting phenomena which appear, which I want to show. So here, this coefficient B, you see it has a jump. If t less than 5, we take 1. If t bigger than 5, so it starts from 2. So B has a jump. so we can regularize it, B epsilon, because I'll show you numerical experiments. So B epsilon is obtained as convolution with Friedrichs modifier, where we take psi to be a function like this. So it is a Friedrichs modifier. So B epsilon is a nice smooth family. We can take initial conditions which will model delta function behavior, so that we can see, look at the propagation of singularity. So we take point singularity. So this is B. So you see there is a jump here. This is a graph of B, and the line, the curve here is B epsilon. And what happens here, I said that we get uniform behavior with respect to epsilon. So U epsilon that we get, you see, it's quite uniform. It looks like there is a limit as epsilon goes to 0. I say it looks like, so there are exact statements which I don't have time now. I think my time is running out. I don't have time to present. So we have this, we have decay properties, as I showed, L2 norm of U epsilon decays, so we can see it also here. But what is interesting is that there is a reflected wave. As I said, echo effect. There is a wave which gets reflected, and we can see it also here numerically. There is a main wave traveling to the right, but then at the point of singularity, you see here 5. The wave, another wave gets reflected and travels in the opposite direction. So it is a reflected wave, and we can look at the strength of this wave, because it's always interesting when there is splitting of singularity, how strong is the new singularity compared to the original one. And here we can see that if you put like very sharp, like delta type singularity in the first wave, then the second wave is also sharp, it's just lower in size. So this is kind of explanation of echo effect, because when the words get reflected by from a wall in echo, as echo, we can still understand these words. So they don't smoothen out. It's still the singularity of the same strength. And let me just show another quick example, because here is a slightly different phenomena, and they are all very interesting to analyze rigorously. So this is kind of tsunami type equation. So this equation comes from, well, it looks simple, but it is one of the models of tsunami or shallow water waves. It's a linear equation here. And so H denotes the water depth here, and U represents the surface displacement. And so if you consider this equation, then again, the question is, what if we have a bottom of the ocean and there is a jump? So there is, for example, some very sharp mountain at the bottom of the ocean. And what happens with the tsunami wave, which propagates on the surface? And here again, so H has a jump, or may have some rock or something. Then we have to interpret this equation in the well, naive way. We have to differentiate H, for example, and we have to multiply it by U. So U, again, we would be faced with a we would have to impose, if you want to stick with distributions, with weak solutions, we would have to impose quite strong assumptions. We would have to a priori expect that the solution should be regular enough. But for very weak solutions, we don't have to do it. So we can even consider H to be like delta squared. We can make sense of it. Now I don't have time, but here we can just think, because we regularize delta by psi, by a family psi epsilon, so then we can think of delta squared being like psi epsilon square. So we have this, and then here again I will show some. So we do numerics, interesting numerics for delta, even delta squared. As I said, delta squared we interpret like phi epsilon squared, where phi epsilon is a modifier for delta. So, and here we have this reflected wave. So the big wave, which is kind of tsunami wave, and then reflected wave. And what is interesting here is that we have reflected wave. So I showed you for acoustic problem, and I said that the reflected wave. So this reflected wave appears because of the singularity of the coefficient. In the classical theory of PDE, reflected waves appear because of multiplicities. Here we look at the strictly hyperbolic case, so the reflected wave appears because of the singularity. And in these examples, it's more regular. So you see that the first wave is like delta function, the reflective is more regular. So it's different from echo effect. In echo effect, the second reflected wave was as strong as the original one, as sharp as the original one, just smaller in size. So here the reflected wave is smaller in size. So you can think that if a tsunami wave is traveling and then there is a singularity at the bottom of the ocean, then there will be reflective small tsunami wave which will travel in backwards in the other direction. And I think that I don't really have time, right? So I have some things to there are some more recent work about hyperelliptic problems which we can do. There are very interesting problems when we combine all this with Fourier analysis and when we consider hyperelliptic questions, because if you consider sublaplacian, let's say, then we have an effect of multiple characteristics going on, which would not be, so the wave equation would not be, so the equation here at the bottom is not strictly hyperbolic, it's weakly hyperbolic, and with variable multiplicities. So we have some effects coming from this. We can also consider higher order equations. You see 2m here. There are also some other interesting effects, and there are quite some papers. So I think I will skip some things because we can combine this with some hyperelliptic analysis and with Fourier analysis on such spaces. So we can put this whole analysis in the setting of Lie groups, like compact Lie groups or nilpotent Lie groups, or this we have analyzed. And there are some things which I'm now quickly skipping. I cannot skip very quickly because my computer is lagging. But anyway, I think I will just summarize here is that the notion of very weak solutions has been invented to deal with equations with very strong singularities. And in the examples that we had so far, we can prove existence, uniqueness, consistency, and then we can study some properties of solutions. We have done this, of course, case by case, because we have to adapt the notion to the equation every time. So there are many interesting questions and many interesting problems. And I think I stop here. So thank you for your attention.
Okay, Professor Ruchansky, thank you very much for this very nice talk with many motivations, physical motivations. So, okay, maybe we have time for some questions. So if someone has a question, please raise your hand and then unmute yourself to make the question to Professor Ruchansky. Any question? Okay, Irfan. Okay, Irfan, could you please unmute yourself and make the question,
Hello.
Professor?
Hello, can you hear me? It's
Yes.
Santiago from Irfan laptop. I couldn't join from my PC. Can you hear me?
Yes, we can hear you.
Yes. Okay. Thank you, Professor, for your talk. I have a question when you talk about the Landau Hamiltonian. Maybe can you go back? If not, I can just ask. But it will be nice if we have that in the screen.
You see my computer is lagging. There is a wheel rotating.
Okay, it doesn't matter then. I just want to ask.
I can go back, but
so-
it will take me it may take me a minute. So,
okay, maybe we wait.
no, just you can start asking and then I will go back.
Okay, so in that problem, you have like the singularities in two different functions. So I guess when you do the Friedrichs type modifier, maybe it would happen that you have two different W's, or how you can guarantee that there exists one W for each type of singularity, or it doesn't matter what Friedrichs type modifier you take, like you can take independently for many different types of singularities, but I think you should get one for all, no?
So we don't have to there could be situations. So the example which I gave were two functions depending on time, right? But
Yeah.
you may have one function depending on time, another depending on x. For example, okay, then these are kind of they don't interact, but you can imagine such situations. So we regularize every function, we regularize separately, and the notion of very weak solution says in this case that there are regularizations of each of them separately, don't have to be the same regularization.
But if it is separately, how you can get well-posedness, like so that because what I understand is you apply the Frick's modifier to the equation, so you get the regularization. Then you will have to apply the Frick's modifier again for the other function.
But we apply them at the same time. So we apply them. Okay,
but independently.
Yeah. So okay, I'm almost there.
So how it will depend, like, for example, the solutions, if you do two different Friedrichs modifier, it will depend on two different W's, no?
So what is W? So we have, there is no W. So we have A epsilon here regularizing A, right? And we have Q epsilon regularizing Q. And for A epsilon, Q epsilon, we find U epsilon. So then if U epsilon happen to be moderate, then we say that the family U epsilon is a very weak solution.
Indeed, but if you the family that regularize A may not be the same that regularize Q, no?
Doesn't have to be the same. Even so, we say.
But you don't need a common one? Is my question.
No. So the definition, if there exist regularizations, because regularizations are not unique anyway. Even when we had only one function A, I was saying that if there exists regularization, and for different regularizations of A epsilon, we get different families of U epsilon. And here for different regularizations of A epsilon and Q epsilon, we may get different families. We get different families of U epsilon. But the question is, when does it correspond? We may get different families of U epsilon, which are different. They're smooth functions, and they're different as smooth functions. So as smooth functions, they depend on the way we regularize, right? So the question is when. So we get two families, and when we can say that these two families are the same in the very weak sense. And for that I give this definition of uniqueness, which was saying that if the difference between how we regularize here, if the difference between U epsilon, difference between two A epsilons, and in that case, the difference between two Q epsilons is negligible, meaning that it's bounded by epsilon to the power n for all n, then the difference between U's is also negligible. So in this case, we say that we have uniqueness. So,
I see, but for example, if you assume the coefficient is the C infinity, I guess you can realize the solution as again a modifier. In that case, which one you will use?
Any. So for
any.
For the existence we have, but it's like for existence we have. So we don't have to regularize it even. We can consider identical. If it's a smooth function, we don't regularize. We just take the family which is equal to this function for every epsilon, or we can regularize. So we can regularize differently, and we get different families of U epsilon. The question is when we can identify two different. So the families which are different point-wise, we can still identify in this sense. It's like two functions which are we can identify functions which are not equal to each other, right? For example, if you have we have functions which differ on a set of measure 0. They are different functions, right? They're different in the pointwise sense, but they're the same in the sense of measure theory. So the same here. We have two families U epsilon, which the family U epsilon depends on the way we regularize. But so for different regularizations, we can get two families of U epsilon, the thing is that how to say that they're the same or not in this, in which sense? So in the sense of point-wise families, they're different. But in the sense of this negligibility, they would be the same if, like here, you see U epsilon minus U epsilon tilde, it doesn't have to be zero, but it has to be controlled by epsilon to any power. So in this sense, the solution is unique.
Okay. Thank you.
Okay, thank you very much. Okay, maybe we are waiting for the next speakers to connect, but it seems that he has some problems with the internet. So it seems that still we have some time for questions to Professor Ruchansky. Any other question? If not, let's say thanks to.
I think there is some.
Okay, so
there is some question in the chat. I see.
In the chat, He said, Carlos said, can you comment about the speed wave in the Landau problem, please?
So speed wave there is so the Q was electric potential. But then we have this Landau Hamiltonian, and then we can multiply it by, there could be some forcing, which is a function depending on t. So we can put it's a wave equation. So there is a propagation speed. So there is, you can think that Landau Hamiltonian gives us electromagnetic field for the medium, but then we start putting particles in this electromagnetic field, and then let's say they are described by their motion described by the wave equation, and then the coefficient which we put there is just the propagation speed, time dependent, like for the usual wave equation. So we just change the Hamiltonian from the classical wave equation to this Landau Hamiltonian and then AFT. And I should say that I gave examples in this talk of the wave equation, but there are results. Similar results for heat equation, for Schrödinger equation. So all of these things work. For more complicated, I mentioned some examples, Sturm, Liouville, and so on. But I would say that if anyone is interested in this, so if anyone likes this talk and interested in the theory of very weak solutions, there is really a lot of open questions, because basically there are many equations and the notion of solution depends on the equation, and we have to find a way how to formulate it for each equation. I gave examples of linear equations, so non-linear, there are only limited results. So there are a lot of problems to investigate.
Okay, Professor Ruchansky, thank you very much for your talk and for your time. So our next speaker is Professor Nikolai Sekov, but we are trying to provide him the tools to allow him to connect. So there is some delay because of this. So let's wait for a couple of minutes to see if we can solve this inconvenience. Okay, so we are waiting for Professor Nikolai Spekov to see if he is able to connect. Okay, very good. I just received one email from Professor Nikolai Spekov, and it seems we will have to reschedule his talk by tomorrow. So to all the participants of the conference, we will send you the program, the update program by today. So just let me say thanks to all the participants that are online, to all the institutions that support this conference, the ISAAC Society, the Colombian Mathematical Society, the Mexican Mathematical Society, the Ghent Analysis and PDE Center, and see you tomorrow in the conference. Thank you very much for your participation today.